Moving right along, let's look at section 9.3, fluid flow. Let's look at some vocabulary terms. The first one is laminar. Laminar fluid flow is fluid flow that is very smooth. Every particle that passes a particular point moves along the same smooth path traveled by the particles that passed that point earlier. The name for that smooth path is a streamline. Streamline is the smooth path that particles can travel in. Each particle follows the one in front of it. Streamlines cannot cross each other. Here's a simple example of laminar versus turbulent fluid flow. I started with laminar flow and now it's turbulent. And now even in one stream of water, you can see at the top that it's laminar, while at the bottom I've got turbulent flow. You can think about lanes of traffic and cars traveling all in their own lane and staying in their own lane, and how smoothly the traffic flows. Those are streamlines. Now, turbulent fluid flow is irregular, it's chaotic, and it's unpredictable. Many features of fluid in motion are modeled with ideal fluids. Ideal fluids have no internal friction whatsoever, no viscosity, and they are incompressible. Water is pretty close to being an ideal fluid for our purposes. Not a lot of internal friction, not a lot of viscosity, pretty much incompressible, at least in the classroom. So it has a constant density. Bernoulli's principle. Bernoulli says, as a fluid flows through a narrower path, its speed increases. As it flows through a wider path, its speed decreases. Since the flow rate is constant, energy for the increased speed must come from somewhere. It comes from a decrease in the internal pressure of the fluid. So when you see a pipe that decreases in diameter, the pressure will decrease. And the velocity will increase. Based on the conservation of energy and pressure included, since a fluid changes shape, work either flows into or out of the system. And again, the bottom line is, as the fluid speed increases, the pressure decreases, and as the fluid speed decreases, the pressure increases. So here, where the diameter is wider, the velocity is going to be lower. And the pressure is going to be higher, which is kind of counterintuitive. Let's talk a little bit about fluid flow within a pipe that has a changing diameter. And what stays constant for the fluid is a certain amount of mass. I want you to try to imagine, if you can, a pipe filled with water, and if you can sort of take, almost if you could freeze the water as a snapshot in time and think about that mass of water. What happens if I take that water and I move it over here? It's going to change shape. It's not going to change mass, but it's going to change shape. It has to inside the pipe. So what does that mean? Mass is constant. Mass is density times volume. The density does not change. The density of the fluid remains constant. Now, the volumes that I have written here are equal to cross-sectional area times the length of the cylinder. So I've substituted for this volume, I've substituted cross-sectional area times the length of the cylinder. And then finally, I'm going to make one more substitution. The length of this cylinder is equal to the velocity of the fluid times time. So I make that substitution here. So it turns out that we've got the same mass in these two positions, but we've got different cross-sectional areas. Let me get this so we can see everything here. Just move this over for a second, and then I'll put it back. So we've got the same mass, but we've got different cross-sectional areas. We've got different velocities. And ultimately, what we have is a certain kind of continuity. We have, if we cancel out density and time from this equation, we have that the cross-sectional area times the velocity is the same everywhere. It's constant throughout the pipe. And this cross-sectional area times velocity is called the flow rate. So no matter where you look in the pipe, if you take the cross-sectional area times the velocity, you get a constant value. Now that flow rate, because it's area in square meters times velocity in meters per second, flow rate is equal to meters cubed per second. And so really there are two ways that I like to think about flow rate. Sometimes it's useful to think about flow rate as a cross-sectional area actually traveling through the pipe at a certain speed. That would be area times velocity. Sometimes it's useful to think about the entire volume, that would be the cubic meters, that are flowing out of a pipe in a certain amount of time. So if you get to the end of the pipe and water is flowing, you might have a certain amount of water coming out in 1 second. And that's another way to conceptualize flow rate. How much water in cubic meters. And remember that cubic meters is relatively easy to change to things like milliliters and liters.